Yes, welcome to the last session for today, my overview of serverless options. So first of all, just briefly, my name is Mattias Jiderhamn. I am working as a consultant at SolidBeans. I'm of course a Java enthusiast. I both enjoy developing in Java and also from time to time speaking at conferences, so much that I've been awarded Java 1 Rockstar. I am available at Twitter. I very rarely tweet, but you can reach me there if there's any questions after the talk. And I also will post the slides and the code examples on my blog. And no worries if you didn't have time to take notes, because I will get back to those URLs later on. So you've probably seen this meme floating around the internet that there is no cloud, it's just someone else's computer. And as we all know, yes, even though it's true, that's kind of missing the point. And I would say you can say the same thing about serverless. Like, there is no serverless. It's just someone else's server. And yes, and that is the point, that it's not your server, that you don't need to manage the server yourself, but someone else will do it for you, and you can just scale out as much as you need. You don't need to worry about neither any physical server or any virtual machine or even the application server that your app is running on. So this is not an introduction to serverless itself, and I'm not going to argue for serverless, but just briefly here, I might interchangeably use the terms serverless, function as a service, and FAS as short for that. So many people view serverless as the next evolutionary step after going from monoliths to microservices, and then we will move on to the serverless era. So we've broken down our monoliths into microservices, and then we break down our microservices even more fine-grained into individual functions that can then be scaled individually. So what I am going to provide you is an overview of different serverless offerings that are available on the market. And we're also going to implement a few examples to compare what you can do with those. First up, of course, we have the big three. We have Amazon with their AWS Lamda. We have Microsoft's Azure Functions, and we have Google's Cloud Functions. They do support a number of different languages. AWS has production-ready support for Java, which I mentioned specifically since this is a Javaforum, but you might as well try out the other languages, of course. In the case of Azure, they do have Java support, but it's still in preview, and there might be changes to the API. So when I was preparing my demo last week, I suddenly experienced they had broken the API, so the demos I had prepared didn't work anymore. So you should be a little bit careful if you go for Java on Azure as of now. Quite surprisingly, Google has not yet released, at least to my knowledge, any Java support in the Google Cloud Functions. They are expected to do so rather soon, but I haven't heard anything official from Google yet. They are, of course, offered in the cloud, and in the case of Azure, you can also run that on-premise via their Azure Stack offering. The pricing model for serverless or function as a service is a bit different to what you might be used to even if you're using cloud services. Instead of paying some kind of fixed fee per hour or so for your virtual machines, you mostly pay per invocation. And then they also made up this new term, gigabyte seconds. So the amount of memory that your function is using times the execution time give you gigabyte seconds, and they will charge you for that amount. And this differs a little bit between the different vendors. So in the case of Amazon, you need to specify a maximum amount that your functions are allowed to use, and then you will always be debited for that maximum amount of memory, regardless of how much is actually used. In the case of Azure, they measure the actual memory usage, and that's what you will be charged for. In the case of Google, they also do the same thing with the CPU, so they have gigahertz seconds that they charge you for also, plus some traffic. And in all of these cases, you also need to have some storage where you store your actual function implementation, so that comes on top of this. All of them do offer some kind of free tier, so you can just create an account and start experimenting with this without it costing you anything, at least for a while. Then there are some challengers. We have IBM, most notably. They have these cloud functions, the same name as Google, unfortunately. We also have something called Hook.io. They were actually the pioneers in this field back in 2014, before AWS. We have something called Web Tasks. We have Spotinst, and we have WebLab. And they, again, support a number of different languages. In the case of IBM, it's actually run on top of Docker. So in theory, you could implement your functions in anything that's possible to run on Docker, but they do support official libraries to help you get started for a number of languages, Java being one of them. From the other ones, it's only Spotinst that do support Java officially. And I think Spotinst is actually a quite intriguing alternative, because if you look at the pricing model and the actual operational model of it, what you're getting is that for Spotinst, you are using the big three clouds. So you can use Amazon and or Azure and or Google Cloud Platform, and then you will have your functions run on their so-called Spot instances. So when they have spare compute power, they sell these for cheap, and then you can buy these Spot instances and run your functions on top of them. So you could probably get some good price for that. I haven't really tried it out, but it's worth to have on your radar, I think. IBM, they also charge you per gigabyte second. And the other ones have some other different pricing models, some fixed prices and some they don't really have that much information on their website, some of these, so you have to sign up to actually figure out what you're getting, it seems. Over at the open source spectrum, we have also, most notably, alternatives from both Oracle, from Pivotal, who are the guys behind Spring, and from Apache. Oracle have their Project FN, Pivotal has Project Riff, and in the case of Apache, it is OpenWhisk. And OpenWhisk is actually the same thing as IBM Cloud Cloud Functions. So they donated their implementation of serverless as open source, which is now driven by Apache, and then they are supplying it as a service to you as IBM Cloud Functions. Behind the scenes, they all use Docker in some form. In the case of Project Riff, it's also Kubernetes on top of Docker. Then there are official support libraries to help you get started building your function to run inside those Docker containers. And they all have official support for Java. And they all use Apache 2 licenses, which may be a bit more interesting now than if my talk had been before the previous one. There are some lesser known options also on the open source arena. We have something called Kubeless from Bitnami. We have OpenFaaS and Fission and Iron functions. All of these also run on top of Docker of some sort. Some of them support Kubernetes, and in the case of OpenFaaS, you can also run it on top of Docker Swarm. Again, there are a number of different libraries that are provided to get you started to build your Docker containers. Only OpenFaaS do supply Java libraries. And they also use some kind of weak copyleft licenses. I think it's worth noting here that all of these different open source alternatives, they do run on top of Docker in some form. And running on top of Docker means that you need to have some kind of Docker host. So you're essentially having a server with your Docker host on. So when we said that there is no serverless, it's just someone else's server, and then if you're running the server with Docker, then there is no serverless, it's just server. So I have to admit, I haven't really gotten the point of it. I'm sure if you get hold of the salespeople, or rather, if the salespeople of these companies get a hold of you, they can surely explain why it's such a great idea to do it like that. But I haven't really figured out the meaning of it. So personally, I like to call this serverless-ish. Anyway, so I will do a bit of demoing on two of those big three that do support Java. So we will be implementing some serverless functions in AWS and in Azure. So you can see the differences and what is needed to get you started. So I should first of all duplicate my screen. And instead of just some simple hello world where you submit your name and get hello your name back from the service, I'm going to do something a little bit more real life. So I have an imaginary XML format with orders, and then I want to have that XML format transformed into another XML format. So I want to change the format of my XML file. So this is the input data that we will be working with, and then I have an XSL schema that is going to perform the actual transformation, and then I have created a couple of Java utility classes that actually input this XML file into the schema. And to get started with AWS, I create a class, of course, and then I will implement their request handler interface. And what I'm going to do now is that I'm going to answer to HTTP queries. And yes, I think we can do that. There we go. Thank you. So AWS has made it a bit more complicated than we're used to nowadays. When we're, for example, implementing REST services, we might be used to just getting the actual contents or our actual entities as the parameters to our functions. However, when you use AWS for serverless, you have to put your AWS Lambda behind something they call an API gateway. So what you're getting as input is an IPA gateway object, and you have to return an IPA gateway result object. And very strangely, at least last time I looked, they don't supply these objects as part of their SDK. So you have to also add these classes yourselves or Google them and copy-paste them from Stack Overflow or something. But I have already these ready-made. So I have API gateway request and API gateway response. So I will implement the interface, and then I had my little transformation service, transform. I will get the body from the gateway request, and this will be my output, but I can't return that one, but instead I have to use this API gateway response, where I get a builder, where I set the raw body, and where I set the status code to 200. So this is my implementation for this service. And now in order to get this running on AWS, I could either log into the interface and use the UI to set up my function and declare the name of the class and different parameters. But I think we want to have this automated by some means so that we can put this in some continuous integration server and so on. And in order to do that, you need to declare an SAM file, so serverless application model. And you can get this file and also some other bootstrapping generated for you using a Maven archetype. But in this case, I have prepared a SAM file where we declare a resource, namely our function, and the type of that resource is a AWS Serverless function. And then we set up some details about it. We set the method that will be invoked. We say that we're running on Java. We point out the jar file. We set the maximum amount of memory, as we talked about earlier, and some timeout that we will get into those details and so on. And then we are ready to actually upload this to AWS. And I won't actually do this during the demo because it takes too much time. So I don't want to keep you waiting. So I have done this already. So you need to do this in two steps. First, you build your code. Then you do a packaging. So you need to have the AWS tooling replace or add in some additional stuff into your template SAM file to get the final SAM file that you can actually execute. But if you're using the Maven archetype, they do add some Maven plugins so that you can do Maven package to get your final SAM YAML file, and then you can do Maven deploy to have it actually uploaded to the cloud. And once it's uploaded there, so I won't press this now because it takes like 30 to 60 seconds or so. Once it's uploaded, I can just invoke this using a curl command. So I'm using this file that we looked at earlier as the input. So I will upload this as the request body. And it will boot up in AWS. And after a couple of seconds, I get my transformed XML file. And now that it's booted up, it's of course much faster. So if we want to take this one step further and say that, well, instead of having to invoke this HTTP service and wait for the result, maybe I can just send it in there, put it on a queue, and then I can have it transformed asynchronously. Yes, of course, we can do that too. So in AWS, we have their simple queuing service, something I'm quite sure it's called SQS. So let's create another function that implements the request handler. And let's listen for SQS events. Sorry, I can't type apparently. And we won't return anything from the function. We will instead send this to another queue. So again, I will take my SQS event. I will get the records. Sorry. And I will loop the records. And for each record, I will get the body. And I will send it to my transform service. And take the result. And then I have an, let's see, Amazon SQS client builder, default client. So I can have an SQS client. I can send that message to another queue. Let's call it output queue. So, and I will take the result of my function and put it on another queue. So I would have to do the same thing again. I would need to declare this in my SAM file. It looks a little bit differently because I need to point out the queues and declare queues and so on and so forth. Then I have already prepared some Java code. Maybe I should increase the font size of this one too. There we go. I have prepared some Java code that puts a message on the queue. So I will just run this one. So it will put a message on the queue that my function that I already deployed earlier is listening to. The function will pick up the message, put it on another queue, and oh, sorry, that was the wrong one. This one. And then we can invoke this other method that pulls messages from the resulting queue and prints the output, prints the body of that message. And what we can see here, ta-da! Now it's been transformed asynchronously for us. Now we can take this even one step further. Instead of having to manage this queue thing, let's say if we just want to upload the file and then have Amazon figure the rest of it out for us. Yes, we can do that too, although it requires a bit more code. So S3, which is the blob storage in Amazon, we can also listen for S3 events. So if something is added to an S3 bucket, we will get an S3 event, and we can loop all those records, and for each record, and there's some, we should by all means get our S3 client. Maybe I should again zoom in a little bit. So we need to get the object from the S3 client, and we do that by first getting the the record has, is it event name? No, it's not. I'm a bit lost. Get S3, get bucket, get name. So here's our in bucket. And then we have yeah, that's, I created a little helper method already where we can decode the key because it has to be URL decoded. So we'll call that key. So we will get the object from our in bucket with that key. So we get our S3 object, and then from the S3 object we can get the object contents, which will be an input stream, and then I can use my little transformer service to transform my content into some result, and then that result I can put on another queue. So I will put object, and I thought I had another queue. Yeah, I think I did like this, in bucket, and we'll just append out to that. We will use the same key, and then we'll create a new byte array input stream with the results. And we need some metadata. I think we can like set content length, something like that. So we're getting an event from S3. Hey, something was added to your bucket. And then we're getting the contents of that item that was added. Then we transform it, and then we put it into another bucket. And I have uploaded that one already. So this is the bucket that we're listening to. So I can just do upload. And I have my, sorry, now I'm in the wrong place. I will just take my input file, blah, 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 blah. So I will upload it to my bucket. There we go. And then I can go and watch my out bucket. And after a couple of seconds, if we pray to the demo gods, there we go. And we have my output file. Sorry, I can't do it like that. We can download this file, and you can see that it's the transformed version. So I didn't have to manage any queues or any requests or just anything. I just uploaded it, and in the other folder, hey, there's my result. So before we leave AWS altogether, if we're talking HTTP requests to AWS, you can also choose to implement them as a regular REST service using Jersey. So there is like a bridge between AWS and Jersey, which allows you to create a REST service like this one. And then there's just a little bit of boilerplate code in between that maps from these API gateway objects into something that can be input to Jersey. So you can have a look at these examples yourself as I'm providing the code at the end. So over to Azure. Let's first do the HTTP version, shall we? Then we'll be using annotations instead. So I will call this one transform. I will have a public, and I think here's one of the, no, this one should be working. And as input to my transform function, I will declare via annotations that I have an HTTP trigger. I will just give this some phony name. I will set that I listen to, sorry, I was imagining post requests. I need to set the auth level to anonymous, so I don't need to add any tokens or something. I can also declare that the data type is binary, though I think that's unnecessary. And then we have one of those bugs I stumbled upon, so I can't actually use primitive byte array, so I have to use uppercase byte to get this working for now. I also will be getting an execution context, and then I can just call my transformer service to transform the input, and there we go. Now, there is tooling for AWS to test your functions locally, though I haven't really spent enough time to get it running in Windows. But the Azure one, I think, is working quite flawlessly. So we can just use Maven Azure Functions run. So we use Maven plugin to boot up our function locally. And it will take, I think, like 15-20 seconds or so. There it's starting the Azure Functions platform, and we can see the URL where our function is available, and then we can make a curl request once again with our input file as input, and ta-da, here's the output as we're expecting. So then let's move on and do another function that we call transform queue. I think I still can return byte array there. Transform queue. And in this case, instead, we'll have a queue trigger where we need to declare a connection. And the default in Azure is to use Azure Web Jobs Storage as the connection. So I'll just use the default there. And then I think we'll need to give this a name. And this one we have to say that it's binary. and I also need to give the queue name. So I have declared a constant up here that says queue input. So that's the queue. And then we will, I think, again, uppercase, unfortunately, byte input. And then we can return the result from the transformer service. There we go. Well, what happens now with the output of our function? Well, we want to put that on a queue also, don't we? Then we just add another annotation. Queue output that again needs the connection. I think we need to set the data type to binary. And then I had my output queue that I call result. So everything is annotation driven. There is still something fishy going on. Okay, that wasn't. No. Let's see. Yeah. Thank you. And we should also have our little execution context there. So something like that. So just by annotations, we're setting this up that we want to listen to one queue and the results should then end up on another queue. Then the Maven plugins will actually produce some JSON settings files that will be actually uploaded to Azure. And you would do that by, instead of doing Azure Functions run, you just do Azure Functions deploy. And again, I won't actually do this now, but I have prepared another little class that I managed to open before, where we simply send a message to a queue. What? I forgot the name. Output. And then we can look among the queues. Oh, I shouldn't talk like that. So here's our message that we just put on the queue. And if we wait a couple of seconds and pray to the demo gods, that one should disappear. And another message should. What? Yeah. So the transformed version of the XML ends up on the resulting queue. So we can do the same thing with the blob store, where we have another function that we call transform blob. We have a byte array transform blob with a blob trigger. Just call it blob. Again, we need to set this connection thingy. And we will set the data type to binary. And then we can say that the path where we will look for new files is the input folder. And then we can also declare the name of the file. So we can get the name as an input parameter if we wanted to. But we will do something else instead. I forgot that one. So again, I will use our transformation service to transform the input. And the output I will send to blob output with the connection, with a name, and data type set to binary, And now that I set the path of the output, I can use those variables that I declared in the input path. So I don't even need to know the name of the file in my Java code. I just say, okay, here, thanks, here are some bytes. Okay, here are the other bytes. And then like Azure takes care of the rest. And again, I have some test code for this, where we add a blob to our blob storage. So, oh, sorry. So I will look at my blobs instead. In the inputs, if I was quick enough, there, sorry. So here's my input file that I just uploaded. And then in the result folder, there's the transformed version. So there's nothing more than that I need to do. Let's get back to my slides a little bit. Like that. There we go. So there are a number of different event sources or triggers that can be used with the different serverless platforms that are out there. So comparing the big three, of course, all of them do support some kind of HTTP requests. In the case of Amazon, through this API gateway service that makes things a bit more complicated. They can all listen to blob storage events. They all have, also you can listen to things that happen in a database. So if you insert a record, then we trigger an event. You can listen to messages. You can listen to streams in the case of Amazon and Azure. Those two also have support for notifications and timely triggered events. In AWS Lamda, there are some specific triggers that only exist there. So you can listen to incoming emails, for example. You can watch the logs in AWS. You can watch for changes to your AWS infrastructure. You can look for Git commits. You can integrate with Amazon Alexa to listen to voice commands in your Lambda functions. They also have some conversation engine. They supply hardware buttons, so you can integrate with hardware and so on. In the case of Azure, they have something specific to them that you can listen to external files. So you can actually monitor like a Dropbox account or your Google Drive or so, and then have your Lambda functions triggered that way. Unfortunately, that's not available for Java, but you need to be running .NET for those. Some general caveats when you're thinking about going serverless. Some things to consider first. First of all, cost management. These services are mostly, as we've seen, pay-as-you-go. So you should try to make some kind of estimate of how many requests am I expecting, for how long do I expect them to execute, and how much memory is it going to need. And in the case of Azure, as we saw, you set a maximum amount of memory, and then that's what you will be billed. And in the case of Azure, you can use their tooling to measure the memory usage on your local development machine. Something that may be a bit counterintuitive is that it might actually be cheaper to go for something more expensive. So in the case of AWS Lambda, if you choose to have a higher maximum memory, you also get more CPU, which makes your function execute faster. So more memory times less time might end up a cheaper bill. You should be very careful with asynchronous operations and background threads that may be started, because as long as those are running, you will be charged your gigabyte seconds. So you should consider setting a low maximum time after which the Lambda engine will just shut down your function. So in case you happen to trigger something in the background that you didn't mean to, you won't be charged that much. I had some problems during testing that it seemed that the boot up time was included in the maximum time. So I had the default of 3 seconds and the JVM didn't boot in 3 seconds, so I couldn't even invoke it once. So that might need some tweaking. Something else to really consider before going serverless is logging. So if you're no longer in charge of your server, then you're no longer in charge of your logs. So you need to come up with some good logging strategy. All of these do provide you in the method signature with some kind of context or execution context, so you can get the logger and log to that one, which isn't very useful because then you'd have to either send that logger around or come up with some thread local or something. So it kind of infects the rest of your code and makes you very locked down to that specific platform. So you should look for some other option. And in the case of AWS Lamda, they do provide a log4j appender so that you can log into their CloudWatch logs. So what you can do then is you use their appender, which does asynchronous logging for free. So you don't pay for that. So you get really low latency. And then you can have that either shipped over to some managed Elasticsearch service, or as we saw, you could have Lambdas triggered by logging events. And then you have some other Lambda where you don't have any latency requirements to ship it off to your Elk stack, for example. For the other services, you might want to consider maybe a TCP appender so that your function is sending directly to your Elk stack. Then you might be tempted for latency reasons to add some asynchronous appender around that. But then again, now we're starting a background thread, so watch your bill before you dare to do that. So you need to test that carefully with the platform you're choosing. Something else to consider is cold starts. Most platforms shut down your functions after a time of inactivity. For Azure, I think it's official that it's 20 minutes. For Amazon, I think there are user reports that it's somewhere around 45 minutes. After your function has been shut down, as we saw when I tried to demo, it can take quite a while for it to boot up again. Up to over 30 seconds has been reported. So you might want to, if there are latency requirements, you might want to figure out some means of keeping your functions alive by sending some keep alive, like ping requests or so, to the number of parallel instances that you want to have up and running all the time. I think Azure does a good job here that you can package multiple functions into a function app. So you can add this like keep alive function, bundle it into your app, so you don't need to change your actual functions to add like keep alive requests to those, but you have this dummy ping thing that you do. There are actually third-party services that help you keep your functions alive and not going inactive. For example, there's something called Thundra at thunder.io that you might want to look up. You may also want to consider the problem with vendor lock-in. All of these have vendor-specific method signatures that you should implement. There's an initiative going on with Cloud Native Computing Foundation. They're working on a standard so that you can have like one method signature and it runs on all the platforms. I don't think there's even a draft yet, so there's a bit into the future. So one recommendation is that you try to abstract away the vendor-specific parts, so you move the actual implementation of the actual business logic to somewhere else and just have the bootstrapping of the platform at that place. Or you don't do it that way, but instead you say, no, I'm going all in. I have chosen this provider and I want to have like all the nits and grits that they can provide. So it's a decision to make which leg to stand on there. I'm really running out of time here, but just shortly, Spring Cloud Functions can help you decouple your business logic from your specific deployment environment by using plain old functions. And I was going to show you a demo where I actually didn't have to do anything because I already had a function. So there's just a simple Spring Boot main application, just does Spring Boot boot. So that's it. And then it just finds the function on the class path and it's up and running. So you can download the examples and try that out yourself. So you're getting a full Spring Boot environment inside your serverless environment with all that dependency injection and everything. And there's some fancy stuff like on-the-fly string compilation and integration to Flux, their reactive streams from Spring. So the demo, I will skip that one, and instead I will just say these final words. Ask not what you can do with serverless, but ask what serverless can do for you. So the idea of going to serverless is not that, wow, I can do new things, I can do these cool things, oh, it will look nice on my CV, but instead, what won't I have to do anymore? I won't need to manage my servers. Maybe I won't even need that queuing system that we saw. I can just upload the blob. So try to figure out what can the platform do for you instead. So you don't need to do a lot of bootstrapping stuff, but you can actually focus on the business logic you want to implement. Again, here are the URLs if you want to continue experimenting on your own, starting from my examples. And thank you.